Alright, this is from George Dishman. There was a post some time ago you can search for. Were right about the cat. There were two previous posts. All the posts. I think the diagram attached to that wraps up what we were saying about aberration. I added your laser numbers, so I hope we agree on what is shown. Can you confirm, please? So this is a discussion I hadn't gotten in on earlier, but basically it looks like we've got a telescope aimed over here and seeing a star that's over here. I don't like the orientation of the telescope compared to the star. What I would prefer is to talk about the image of the star. This is incorrect to say this is the position now. The position, or well, I don't know where it is now. Position when the light was emitted, this is the part that's incorrect. If the orientation of the telescope catching ray 1 through the objective lens to the ocular lens B if that's the orientation, that means that the position when the light was emitted was over here. The fact that they are putting the position when the light was emitted over here means that they do not have a basic grasp of the relativity of position, which states basically if you're using either kind of relativity, Galilean or relativistic, you're using something called the Galilean transformation. Say I'm here on Earth, standing here looking up at the sky, looking at this star at x equals 0, y equals, I don't know, 100, and let's say it was 10 years ago, so I'm going to put negative 10 in here for the time that that light was emitted. Okay, then I accelerate over here, giving myself a velocity plus 10. Now, x prime is x equals x, which was 0, minus 10 times negative 10, which is going to be positive 100. That star just moved. So the new position of the star is way over here. Way, way over here. Okay, so that's what bugs me about this diagram, that it does not seem to indicate the relativity of position. And if the telescope is pointed that way, the reason it's pointed that way is because the actual light was emitted way over here as soon as we change the velocity of that object, the observer. I seriously hope that recorded because my timer says 3 minutes and 30 seconds and it felt like a longer explanation than that. But if it didn't, I'll come back and record it again. Second, he posted a graphic in a post you can find by searching for "in the meantime." The attached diagram should explain how I view this. The relevant part is just the paragraph starting with that phrase and the following paragraph plus the image they relate to. Do you follow what I'm illustrating there as proper distance? This says, if we consider the dot of the local observer at O to contain or be a wide binary star system, the two stars shown as orange lines in the attached diagram would have some finite separation as measured locally. So hence not Hubble observers. They would have finite separation as measured locally. For the sake of argument, we might take that to be some light years, certainly much greater than the size of the components, and the system has been stable for most of the history of the universe. An observer in a nearby dot C will see that separation due to length contraction as shown by the superimposed green grid lines, but the same geometric scaling will also apply to the diameter of the stars along the line of sight. Actually, you'd be surprised. The spheres actually don't. Spheres actually remain spheres under Lorentz well, once you take into account the optical effects that the spheres will actually don't change shape, but what they do like if you have design on the sphere, then I think that the design on the sphere will aberrate in the direction. If the thing is accelerated that way, then all of the design will kind of scrunch forward into this part. So it stays spherical, but you can actually see the back surface, or the part that's coming toward you. You can see the back surface of it coming toward you. And when you look at the back end of it, well, you don't see much light coming from it at all. You can actually see this on my spoon-fed relativity site under the essay and article Penrose-Terrell rotation. Not a very exciting title, but there are videos and animations during a conversation about Penrose-Terrell rotation at physics forums. And I made a number of animations here kind of showing how a sphere, well, a group of packed spheres would appear. And what I found was that the actual spherical shape of the spheres seemed to maintain pretty well, and that but you do see I guess you do see kind of a contraction there, but they do seem bigger as they're coming forward somehow than they do when they contract. But the actual spherical shape, I forget how fast this was set to, but it was really, really fast, like 99% of the speed of light or something like that. The distortion, vertical distortion, I guess, were these all using the same speed of light? Why do I not have the speed of light, the speed marked here? Yeah, sphere animation at 0.99 C. Still looks like a sphere. That's what it was. The actual individual spheres were just using internal Mathematica representation of sphere, but the actual coordinates of the centers of each sphere was done with Lorentz transformations. So you can see that the actual spheres do continue to look like spheres. Okay, similarly, an observer at dot B will see the smaller separation because his blue axes are more steeply inclined with A. We'll see the smallest separation shown by the magenta lines. In Jonathan Doolin's model, there is an upper limit to that effect. The asshole. In Milne's model, there is no limit because his model has dots infinitely far away. Why Jonathan? I don't. Just stop lying is all I have to say. Stop telling people that I'm saying things that I'm not saying. Why Jonathan thinks the Planck length is relevant is puzzling, as the distance between stars is not affected in any way by whose axes are used to quantify that distance. I can only think, well, yeah, stop lying about things, George. I have pointed out that I don't believe that the Planck length even exists, so that's why I brought it up, to point out that it didn't exist. It's not relevant. It doesn't even exist. Is puzzling, as the distance between the stars is not affected in any way by whose axes are used to quantify that distance, I can only think that Jonathan is treating the selected observer as a privileged frame in some sense. And again, since George is just creating a straw man, I don't see why I don't enjoy responding to him. What's interesting to me here is that instead of trying to clarify these things with me, he kind of is addressing this to George. He's telling George that he's trying to misrepresent my ideas to George so that George will think that I am incorrect, which is kind of frustrating. And I think I said that wrong. George is trying to misrepresent my model to Paul. Paul, I think, has been pretty well trying to understand what I'm actually saying, and can understand that I already said that the Planck length is irrelevant if he read what I said. And specifically, I don't believe the Planck length exists because here's what I said. Planck's constant was actually invented by Planck and is good physics. However, if anyone advocates for Planck mass or Planck length, they cannot self-consistently advocate for the infinite Lorentz transformation. When asked about Planck length from my students in physics and astronomy, I usually describe how it is derived, essentially by setting the wavelength of a proton, replacing the radiant energy with the associated mass energy. This part, I tell them, is in error. Lambda equals hc over mc squared, and then give the equation for the Schwarzschild radius. And I might mention to them that the Schwarzschild radius is an approximation, and I'm not all that certain whether it is a good one. Then set lambda over 4 pi is greater than r sub s. Then I show the waveform for the wavelength of the sinc function to explain why to divide something around 4 pi. Then solve that equation for the mass and plug r sub s in or lambda over 4 pi. In any case, the most important part in this derivation, in my opinion, is the mistake of setting the photon's radiant energy equal to some mass energy, rest mass energy. Without that error, there is no Planck length. There is no Planck length because the thing that creates the concept of Planck length is an error. So to say that I am claiming that the Planck length is relevant is absurd. I didn't just prove that the Planck length was irrelevant. I was proving that the Planck length is just is an absurdity. Ah well, I guess I gotta get going.